So today I will be talking to you about memory safety, everyone's favorite topic when it comes to languages that don't have a garbage collector. What exactly is memory safety? Among other things, it is accessing memories that you have allocated in your program that is not going out of bounds or not freeing memory that you don't have. And whenever you're allocating memory, you're ensuring the program that you free it later on. So if you look at this function here, can already see that we have a malloc here, which is allocating some memory on the heap with buff size, and its malloc by default returns a void pointer, which is a pointer to some unspecified type of memory. That's why most of the time you'll see void pointers get casted into a specific type of pointer, which in this case is the character pointer. So we can outright say that this function is not memory safe because there is no place here in this declaration that we are freeing this malloc. And we've been taught in school that, or by courses, that if you have a malloc, there must be a free. So there's this relationship established between allocation and deallocation, right? It's symmetrical. There's, if you're gonna have a malloc, you should have a free. But trying to maintain this mindset is incredibly tedious and error prone. And this is actually why a lot of people don't like manual, air quotes, manual memory management, because this is extra overhead that you're trying to maintain and keep track of while you're doing the rest of your actual logic. But if we even look further into it, this relationship, the symmetry between allocation and deallocation is too granular and only really works for smaller scopes. The moment that you try to deal with nested amounts of allocations and deallocations, it's really easy to lose yourself in that. It's too simplified in the sense that you just think about it entirely in the symmetric relationship that malloc and free has. You tend to miss a very important pattern that we will talk about later in the presentation. And it should really be abstracted out. And when we abstract this out, we achieve memory safety by design. That is, we eliminate a whole entire area of bugs simply by following a design that we have set out that deals with this relationship. In fact, a reason why people like garbage collected languages is that this entire relationship between allocation and deallocation does not have to be dealt with by the developer themselves. It's abstracted out from them, and hence they get a reasonable degree of memory safety. That is, they don't really worry about use after freeze or double freeze or dangling pointers as much, even though they can definitely still do that if they somehow mess it up with the garbage collector, which is like accidentally holding references that don't actually get used. But really, it's never been about allocation and deallocation specifically. And this is the pattern I was talking about that you kind of just miss if you think about it that way. It's about lifetimes. You'll find it becomes significantly easier to grasp the concept of memory safety by thinking of when should your references be valid and grouping together references that share the same lifetimes instead of trying to think of them individually. So if we go back to our function earlier, uppercase, we'll see that we now have a pair, a free, but it's not in the same function because we can't free it inside there because we need this allocated result to be alive by the time the sprint happens. And we see that this lifetime of this result starts from the uppercase function and it should end after printf. This idea of where to place the malloc and the free just comes with the idea of thinking about when should this allocated memory be alive and when should it not be alive anymore. So if we execute this, we should get what we expected, which is hello world, what's uppercase. So more on this idea presented earlier in lifetimes, that is, we group together references that share the same lifetimes. A good example of this would be structs. If we were to declare resources inside structs, we would need to be allocating them together and we should be freeing them together because these resources wouldn't make sense to be around when the struct itself isn't around. We look at the C code example. Sorry if the code background is different. So we see here that we highlighted the mallocs and the frees. So first we allocate enough memory for the node struct itself, and then we allocate the contents. So we allocate the name, then we allocate another node, a list of nodes that it should be pointing to. If we create that, if we create that struct here, we end up having to free the allocated attributes first, and then freeing the entire struct itself. So you see how this could be confusing, because whenever you declare a struct now, there's this implicit agreement that you have to free these three after it. And kind of messy. So people smarter than us have already figured out a way to deal with this, and it's in a pattern abstracted through, of course, objects. It's called RAII, or RAII. It's resource acquisition is initialization. You look at these two pieces of code here. One on the left is C++, and one on the right is Rust. And you don't have to know the specifics about the language, but the pattern here is what's important. If you've used C++ before, though, you know that a lot of the things there are objects. And a big reason for that is a language feature of C++ is that whenever an object goes out of scope, it will call a destructor. And whenever you create an object, you would call its constructor. And here we have the constructors here in node string name, name neighbors. All that does is just initialize the name and then the vector, that's the neighbors. And then we give it a vector of neighbors immediately, it just initializes that as well. So the idea here is whenever we create a node object, it would create the strings and the vectors. And these strings and vectors under the hood, they would have their own destructors that do the freeing of the memory. And whenever an object gets freed, its destructor gets called, the default behavior of that would be to recursively call destructors of its inherited, or like if it of its attributes. So if whenever this node gets destructed, it would also destroy its string and its vector attributes. And you'd see that behavior in Rust as well. If we don't mind the nested types here, that would be just for mutability. You'd see here that we don't call free as well, and that's because this is already implicit in Rust that whenever an object goes out of scope, it gets dropped, or that's just another term for free, and it gets everything related to it deallocated as long as it owns it. Really, the important pattern here is this, which is whenever you create an object and it holds onto resources, when the destructor gets called, you need to free those resources in there. That's the idea of RAII. Now, this works. This works for the most case, but you'd see that this would get a bit annoying to work with because of the constant wrapping of resources just so that you can group together things that you want to free together. Object lifetimes are simpler to manage than individual lifetimes. We are grouping together lifetimes that are relevant to each other and then freeing them together at the end of the lifetime of the object. Moreover, Rust's memory safety can actually be attributed to it enforcing essentially a stricter version of RAII with the following rules. That is, each value has an owner. There can only be one owner at a time. And when the owner goes out of scope, the value is dropped. These are enforced by their compile time borrow checker. C makes it easy to shoot yourself in the foot. C++ makes it harder, but when you do it, it blows your whole leg off. But Rust straight up just takes your entire arm off. But objects aren't a C feature. How am I supposed to take advantage of this pattern in a language that doesn't even have the capacity to do RAII? RAII isn't the entire answer, but it does show us the pattern we can take advantage of to get memory safety by design. First, a review. Malloc and free are generalized interfaces over memory. It's portable and applicable to most use cases, but it does struggle to stay reasonable in scenarios that require specialization. And that makes sense. If it's made for a general scenario, it's not going to be able to do optimizations specific to your use cases. And it's fair to say that RAII is a specialization of this interface. Will limit the interface and how it deals with the symmetry of lifetimes, that is, by only allowing the references to be valid while the object is valid. Objects aren't what makes RAII work. The idea of setting regions in your code in which groups of references can be expected to stay in their shared lifetime. They should be valid within these bounds and invalid outside. These regions have manifested in RAII as the lifetime of an object, dictating the part of code in which its allocated resources are also valid. And now we find ourselves at the precipice of human ingenuity. Arena allocators, or simply arenas. So here's the plan. We prepare a big buffer using malloc, and our future allocations go in this pre-allocated buffer. This is going to be the start of our valid region for this lifetime. Whenever we need to allocate resources, instead of using malloc, we use a function we define to push our required memory onto our buffer. And when we deem that the lifetime should be over, we simply free the big buffer itself. This is the end of our valid region. Not only does this approach emancipate us from the forced symmetry of malloc and free, it is also much more efficient CPU-wise to free memory in bulk. In fact, you've already been doing this. The stack handles memory just like this. Whenever you enter a function scope, it pushes a frame onto the stack. And then whenever that function is over, it just frees that entire frame. We can use that pattern to dictate lifetimes. So here's an implementation of that plan. So here we declare a struct arena with a void pointer to a stack. And again, this is a void pointer so that it allows the caller themselves to assign a type to the pointer that they're going to be getting. This would be equivalent to just using generics essentially. And we keep track of the current index where we are in the stack and as the size of the stack so we can avoid overflows. Next is we declare the arena creation function with a size. So first is we allocate memory for the arena itself, for the entire struct, and then we allocate memory for the stack. And this is where the actual size goes. And then we assign it initial values to it. Then we return that arena. We also define a destroy for the arena, and this is where the freeing happens. So you notice that we are only really freeing the stack and the arena itself. So if we did allocate memory onto the stack, we would be freeing everything in bulk. And now here we define our arena alloc. This would be a replacement for malloc, and it takes in an arena and the size of the memory that we want to allocate. So how would this look like? We first check if we have enough size for it, and then we increment the index by the size that we want to allocate, and then we return a pointer to the start of that allocation. This is how we would go about using it. First is we declare the start of the lifetime by creating an arena with a specific size. So you can think of this as allocating a bunch of memory up front, and this is the start of our lifetime again. So all allocations paid with that arena will be valid while that arena is alive. So we can use it as a malloc substitute here, wherein we just pass in the arena along with the size that we want to be allocating, and then we cast it just like how we did with malloc because it's a void pointer. We can reassign it because again it's our own pointer now, and then we can use it just like any other pointers that we have allocated with malloc. And better yet, arenas are composable with your code as long as your definitions of your functions take in an arena in which they would use that arena for their allocations. So here in uppercase, we now take in an arena parameter. Oh, I didn't get to highlight that. But we take in an arena parameter here. It would use that to do an arena alloc within the function itself. And another benefit of this would be that in your code, you would be able to immediately tell which functions do allocations because they take in an arena, right? And after we do all of our things with our arena, we can just destroy it. It would free the stack and everything that was allocated on it, and then it would also free the arena itself. So all of the allocations made with the arena will be invalid right after we destroy the arena. And nothing is stopping you from further specializing this arena for your own use case. So you could allow popping the topmost allocation. This would be just in parallel to the stack frame analogy earlier. And if our arena has the same type or the entire like region that we've allocated, we can do this thing called pool allocator, wherein we could pop anywhere in the allocated memory as long as we have pointers to our next valid or next free memory for our pushing. This would add, of course, extra attributes to our arena, which is that it would have to maintain a list of the free areas in our arena. And if they aren't the same size, you would have to implement your own defragmentation algorithm. And this actually also applies if you wanted to use dynamic arrays inside of your arenas, because if you aren't aware, vectors, whenever they hit their size or their capacity, they have to reallocate or essentially move pointers. And what how this would work in an arena is you'd have essentially a dead code in that arena, which is the first dynamic array. And then whenever it gets reallocated, it would just get pushed on top of the new arena. And if the size of your arena is constrained, this would be essentially costing you more than just using malloc and realloc. But you would lose the benefit, all of the other benefits of arenas if you did go back to malloc and realloc. Most of the time, that is overkill and linear allocation is good enough. Again, back into the dynamic array example, you could just do all of the pushing and the popping before you push it into the arena. And whenever you put it into the arena, that's essentially an agreement that this is going to be a static arena. Moreover, you can also declare a static arena. This is different from static arrays. Static arenas are arenas that have the same lifetime as your entire program. So you can use it as a default arena for your allocations if you're lazy to define arenas within scopes. And then you can also declare scratch arenas, which are function scoped arenas that are used for temporary allocations. That is, if you're inside an arena, you can make arenas there, and then you can use that essentially as a lifetime within that function. And then whenever you're done with your allocations inside that, you can just free that scratch arena and go back to your upper scope and so much more. I think arenas are so handy that there are some non-garbage collected languages that actually implement them in their standard library, such as Odin and Zig. And in Zig, we have this implementation, which is we would have to just declare an arena allocator, and we initialize it with a child allocator, which is essentially the malloc that we're using in the C implementation. We can hot swap what type of allocation we are going to be using. So in this Zig example, I'm going to be using a page allocator, but if I wanted to use C's malloc, I could do heap.raw C allocator, and that would use malloc under the hood. And then here's that allocation. Another cool thing about how Zig implements it is it has a defer keyword, and if you've done Golang before, what this does is it would execute this arena.dinit or the destroy function right after this scope expires. So after main, it puts in the arena dinit call, ensuring that the arena gets freed. So here we access the allocator that our arena is using, and then whenever we pass it as an argument to a function, we can use it to allocate within that arena, and it gets freed. Arenas are really cool because they're one of those few things in computer science that induce an entire mind shift change when it comes to memory safety. It's much less of a daunting task to handle memory yourself if you're grouping together things that are relevant to each other and then freeing them in bulk. And I hope that I was able to impart that information upon you because I've been enjoying using them. Thanks for watching.